Okay, and I will start to share my screen with you all. Mhm. Great. So start here. So guys, in the last class, we finished talking about diagnostic horizons in the WRB that's express accumulation of matter, or the accumulation of some solid particles, organic or mineral solid particles by transport, by movement, by migration of material, or because some particles can be wafered and destroyed, and then you concentrate some elements and some minerals. I think that someone forgot the microphone open. It. Let's just check. I will close it. Okay. Okay, great. Just to be sure that. Okay, great. Thank you. And then let's return. Okay, great. So then we saw these horizons that could express accumulation of matter because of any transport or movement of particles. For example, we know that we have the RJ horizon that could express migration from clays from the E or A horizons to the B horizon, okay? But also we have the Ferhalic horizon, for example, that express a concentration of material because other minerals are destroyed, and for example olivine, pyroxene, and even kaolinite could be destroyed, and you concentrate iron oxides, aluminum oxides as an expression of a deep and intense wafering and leaching. Okay, so now let's see other diagnostic horizons that does not express accumulation of matter, or horizons that also express soil formation, but they are related to other properties, none of those that we mentioned before. Okay, so first of all, the Albig horizon, and the Albig horizon, it is the diagnostic horizon that usually fits this E horizon that we can see here between an A and a B horizon. Okay, this Albig horizon is formed by intense destroying of clay fraction, or of course it's much more common, the migration of clay. So clay, we already know that clay can easily migrate from a horizon to the deepest horizons in the soil, and because of this intense movement of clay, some zones, some sections in the soil can register a white color, whitish colors, sometimes some grayish colors too. Okay, so this destruction or migration of clay can get a whitish color in the horizon because of what really gets color to soil. It's clay, okay, mineral or organic clay, both they color the soil. So without clay we don't have a strong influence of any material that can get any color in the soil. And this whitish colors that we can see is related to the quartz grains that has a translucent, they don't have they don't have actually a color, but we usually see them as a whitish, grayish colors. Okay, so the absence or at least a very low content of clay usually express these whitish colors with high chroma and high value. Okay, so let's see the diagnostic criteria for the Albig horizon. The Albig horizon should express cleric material, and cleric material, according to WRB, it's described as a material with whitish colors. So it should register high values, and or the color of the soil should be connected, directly connected to the sand fraction. So you need to think about the horizon, which colors are connected to the sand, not to the clay or silt fractions. Okay? And we need to find one of these A or B action statements that this Albeck horizon, it's over an Arctic, Natric, Plantic, or Spodek horizons. So one of them, okay? And it's quite easy to understand why, because we usually, when we have a E horizon, it's because something below it receives clay. So we register some of these horizons that could express this clay migration. And the letter B, the other option, is that this Albeck horizon forms part of a layer with stagnant properties. Okay, stagnant properties I will show you in the next few slides, but we can just consider that one of these two options is okay. And in the last statement, this last criteria is about thickness. So the thickness of an Albeck horizon should be equal or higher than 1 centimeter. So let's see what are stagnant properties, okay? Here we have the glaic properties that are much more common, and we usually are more used to them. Glaic properties, they are connected to features that express the water table fluctuation, okay? So let's think about lowland, and on this lowland we have a river, and this river, it changed its volume and the water table level according to the season. So in the dry season, the water table level could be very, very low, but in the wet season, because of the rain, the water table level increases and go upper, close to the surface. Because of this movement, during the wet season, this water table, it reduces some parts and some sections of the soil. So you have this grayish colors that you can see here, okay, and here too. And because of the water table fluctuation during the wet and dry seasons, you can register some oxic features, okay, some oxic concentrations like iron, especially iron concentrations, but we also can see sometimes manganese concentrations. So you can see some red, yellow, and black or dark dots, okay? And they usually are connected to voids. Like here, you can easily see that these biopores, pores created by biological activity, they have a ring, like a coating of oxic features. So because of the roots that are growing here, they produce oxygen, and oxygen also can enter from the atmosphere to these voids easier than in the rest of the soil. And because of the oxygen in the voids, we have a ring of oxic features. We have a ring of oxic conditions. So the soil has this grayish color because of the dominance of iron 2, dominance of reducing conditions, but in the voids we have some oxygen that could produce oxic features, could oxidize iron, and then we have iron 3, okay, with this reddish, yellowish, and sometimes dark colors because of the manganese too. So glaic properties, they express variation of water table level, and we have a grayish horizon, a grayish layer with some oxic features, and these oxic features, they are connected to the voids, expressing presence of oxygen only in the voids. So we have a restrict presence of oxygen that it's only present in the voids. The stagnant properties is the opposite. These technical properties you can see here, okay, this is a very typical horizon with stagnant properties. We have now some reducing conditions, but now these reducing conditions, they are connected to water that came from the upper horizons to below. So let's think about a soil that could be, for example, it's quite common in dry lands, okay? So we have heavy rains, torrential rains in the wet seasons, and when water starts to migrate, to penetrate through the soil, this water can achieve a layer that avoids water penetration, a very low porosity and a high bulk density. And because of this high bulk density, water cannot penetrate through the horizon. So during this, the water can saturate the voids, the pores, and then the water can start to reduce some iron and or manganese. So you can see in the voids some reducing features, and inside the aggregates, you still with the oxic iron. So you can still in this inside the voids, inside the aggregates, I'm sorry, inside the aggregates, you still have hematite, goethite, and also other iron 3 minerals. But in the voids, you register iron 2 because of the reducing conditions. So the stagnant properties, they are the opposite of the glake properties. You have reducing conditions only in the voids, only between the pads, between the aggregates, okay, and the space between them. So you have like some lines, as you can see very easily here and here. You have some lines that express the voids, the connection between the pores, and then there you see these grayish colors expressing the reducing conditions. But inside the pads, inside the aggregates, like here, you still have the oxic iron, okay? You still have iron oxidized, you still have iron 3. So it's the opposite. In the glake properties, the water comes from the bottom and achieve a section, reducing all that section, reducing all that layer, all that horizon, and you have a dominance of grayish colors with some red or black dots. In the stagnant properties is the opposite. You have iron 3 as a dominance, and you have some lines expressing the cracks, expressing the voids, expressing the pores in the soil with grayish colors. So it's the opposite, okay? So again, these stagnant properties, they could be one of the criteria to identify the albic horizon, okay? Oh, here are also other photos that could express, that could show to you, okay? You can see here a void with root, okay? And in this void, you can see this grayish color. It's quite easy to see. You have this yellowish color here, and inside the void, you have this grayish colors. Here is the same, okay? So we always see these grayish colors only in the voids, expressing these stagnant properties. Here is the same photo with higher magnification. And now let's see another horizon. The Pompeiic horizon. The Pompeiic horizon has a very interesting connection with geomorphology, okay? Pompeiic horizon express buried surface horizons. So we have a past Molic or Umbric horizons, and these horizons, they were buried in the past because some mass movements, because some addition of fluvial deposits, or even because of humans, but they were buried. Okay, so the Pompeian horizon expressed like here you can see very easily here and even here these darkish colors expressing horizons that were formed at the surface in the past, but they were buried after that. Okay, they are quite interesting because, for example, we can date these horizons and we can know when they were buried. And this information is quite interesting if you are studying the connection between geomorphological evolution and soil evolution in one specific landscape. Okay, I like them very, very much because of this straight connections that they can do for us between landscape evolution and geomorphological process and soil formation. Of course, we need some criteria to identify the Pompeian horizon and to differentiate them from, for example, sunbreak horizons, for example, from other horizons, some spotted horizons. So, for first of all, to identify a Pompeian horizon, it should be a buried surface horizon, and the content of organic carbon should be equal or higher than zero point 0.2, and of course less than 20% because we are talking about a mineral material. Okay, and the content of soil organic carbon should be equal or higher, 25% higher than the overlying layer, and 0.2% higher than this overlying layer, but depending on relative and absolute contents. So when I compare this, the content of this bare red horizon with above, I need to consider in a relative way, considering 0 to 100%, and here in an absolute way, like the addition. Okay, so let's see that, for example, a Pompeian horizon has 0.3% of organic carbon. This overlying horizon should has 0.1 or even less than this in an absolute content. So I can fit this, and then I can just calculate 0.3%, it's 100%, 0.1, it's equal to X, this is equal to 33%, so okay, fits also this criteria of a relative increase of organic carbon content in the Pompeian. This criteria is just to express that, of course, what we have below is a buried horizon with darkish colors, but much more important than this, with a higher organic carbon content than the overlying horizon. Okay, we need to register a lithic discontinuity, okay, in the upper limit. So to express that this horizon were was buried in the past. So we have some criteria to identify lithic discontinuities, and the most common is variance of sand contents. We can calculate some ratios between coarse and fine sand, coarse and medium sand, silt and clay, and some descriptions of rounded and non-rounded gravels in the soil profile that could express some migration, some transport of material. And the last criteria is that this Pompeian horizon should register a thickness of at least 5 centimeters. Okay. Oh, we also have the Nidec horizon, and this Nidec horizon, it's quite interesting because it has a huge amount of shiny faces. We have a lot of clay skins on horizon. So, of course, on photos, this Nidec horizon hardly can very easily identifiable because we cannot see very easily these shiny faces when we check the soil profile at that way, but when we are close to the pads, we can easily see the shiny faces. Okay, the nidec horizon is different from the argec horizon because the nidec horizon it must register a clay texture. Okay, cannot register like a loamic texture, for example. No, the nidec horizon should register a clay texture. A lot of people talks about the formation of this nidec horizons, and some of the hypothesis is that this nidec horizon registers low activity clays, but because of the high content of clay, will have some shrinking and swelling process that could orientate some clays at the surface of this aggregates or pads. And because of this orientation, we have this clay skins, okay? Also, some people, they said that the nidec horizons, they are more connected to mafic materials. So, for example, some basalts and gabbro and other rocks that are quite rich in mafic minerals that could be easily weathered. So these intense destruction of minerals, of primary minerals, can produce a high amount of clay. And because of this high amount of clay, we register some clay skins, okay? Also, some people says that the nidec horizon, as the argec horizon, also register some clay migration, some clay elevation, but because of the very high content of clay, you cannot register the difference of clay content between the B horizon and the overlying horizons, okay? So because the nidec horizon, it's usually connected to mafic materials, you have very low sand content, very, very low. And it's quite easy to understand why, because these horizons, they are formed from rocks that virtually are absent of quartz. So without quartz, they cannot produce sand fractions because at an intense condition of weathering and leaching, these minerals that compose these rocks, they cannot survive for of the weathering from intense chemical and physical weathering. So because of this intense chemical and physical weathering, all the minerals are destroyed. Without quartz, you cannot produce a huge amount of sand fraction. And because of the dominance of clay, even with the clay migration, you produce the clay skins, but you cannot produce increase of clay content in the overall in the B horizon compared that to overlying horizon. Okay, so if you don't remember, these are
Uh,
the clay skins. Oh yeah,
Professor,
yeah, yeah,
uh,
yeah.
this referring to the metrical horizon
Oh
are using
yeah, 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 yeah.
yeah
Good question. Good question. It is
are
quite
referring
different from the metric horizon. Okay.
yeah. What is the difference?
Oh, the
This
difference that
this metric horizon, these are used yeah
Yeah,
WRS,
yeah,
no?
yeah. Oh, okay, okay. Let's see the differences, okay? Because we have a lot. The metric horizon, if you can remember, it is especially formed in dry lands. Okay, so because of the concentration of sodium and salts, especially sodium salts, at the surface, you have some chemical dispersion. And because of this chemical dispersion at the surface, you have some clay movement, some clay elevation from the A horizon to the B horizon that could form clay skins. But much more important than this, you create a huge difference of content between the A and B horizon. So you have a huge amount of clay in the B horizon and a very low content of clay in the A or even E horizons. Okay. And also the nitric horizon, you could register a higher sodium content and sometimes even a darkish color than the A horizon, because this chemical dispersion destroys the aggregates in the A horizon. And because of this destruction, you can release some clay, but also some organic matter. So you register a lot of times you can see darkish colors in this nitric horizon because of this clay movement and because of the organic matter movement that's connected to a chemical dispersion of aggregates because of salt and especially sodium precipitation at the surface. The nidec horizon is the opposite. It's more connected to wet conditions, wet and tropical conditions, okay? This wet tropical conditions produces an intense wafting, an intense leaching, and an intense destruction of primary minerals. And this intense wafting and leaching does not concentrate salts, especially actually it's the opposite. They have an intense leaching of uh, primary minerals and intense leaching of bases. So you cannot see like high contents of sodium or potassium because it is a soil that was deeply wafted and leached. Okay, so in this case, this clay movement, it's more connected to this shrinking and swelling of aggregates at the surface because change of wet and dry conditions during the seasons and especially during the days as the Arctic horizon. But as I said, you cannot calculate a huge difference of clay content between the A and B horizons. And a lot of people, this Nedic horizon still have some discussion about its genesis because we have some process that seems to be connected to the genesis of Nedic horizons. Some peoples, they usually shows that this Nedic horizon is more connected to clay format in situ, clay format in the B horizon. So we cannot see a lot of alluvial features or alluvial features that express clay migration in the Nedic horizon. We can see, yes, we have some Nedic horizons with clay coatings and infillings, especially seen in thin sections at the microscope scale. But the majority of the Nedic horizons, they are more connected to clay format in situ. And this clay is orientated because of the shrinking and swelling. So because of this movement and because of the high content of clay, the clay tends to be orientated at the surface and then express what we call clay skins, okay, or these shiny faces. Okay, now is it clear the difference?
Yeah. Prof.
Oh, great, great.
Thank you.
It's good. It's good because they are quite different. They are quite different. So again, here you can see this clay skins very easily. And the criteria to identify Nedic horizon, it's you need to register at least 30% of clay. As I said, you cannot see a Nedic horizon with a high content of sand or silt. And this, it's straight connected to the material that we saw, these mafic materials that, as I said, produce a high content of clay because they are composed by several minerals that can be easily destroyed. Okay. And also much more important than this clay content, we have a single or a combination of A and B. First of all, a moderate to strong angular or subangular blocky structure. It's quite common to find subangular and angular blocky structure in Nedic horizons. And the structure should register a grade that's classified as moderate or strong, okay? Why we are saying that? Because of this high content of clay. Because of this high content of clay, we register a strong aggregation, a strong pedalization. So we can see a very low content of clay that is not composing the pads, is not composing the aggregates. Actually, the majority of them, it's composing the aggregates. So we register the moderate to strong structures. If you don't know, moderate and strong structures, they are described as the person, considering the percentage of materials, of particles like sand, silt, and clay that are in your hand when you take some samples. So you can figure out that you are in the field and you are taking some hand samples in the soil. So you can check in your hand after hit the soil samples with a knife very gently. You can check if you have a lot of particles that are not composing pads or aggregates, so you have a weak structure. If you register more aggregates than dusty, and then you can register moderate structure. If you basically don't have any particle that's not composing aggregates, so you just have aggregates and pads in your soil, so you register a strong structure. So it's a quite easy and fast way to explain this weak, moderate, and strong structures, but basically they are connected to the difference of dust and aggregates that you can take from the soil, from one specific section of the soil, okay? And because of the high content of clay in the netic horizon, we must register a moderate or strong angular or subangular block structures, okay? And these structures can break into polyhedral or flat edged second level structures, okay? So you can see some prismatic structures, for example, okay, at secondary level. And we have in all of these structures shiny surfaces, okay, shiny faces at a minimum of 25% of the faces, okay. Or the other option is to find polyhedral structures like the prismatic one with shine faces, okay. So we must register blocky or prismatic faces to prismatic structures to identify the netic. In both cases, we must find shiny surfaces or shiny faces, okay, in at least 25%. The other criteria is number 3. I need to find A, B, and C. I need to identify at minimum content of iron extracted by ditionite of 4% that we call free iron, iron that composes the iron oxides. We need to register at least 0.2% of iron oxalate, iron extracted by ammonium oxalate. That's the iron associated to low crystalline minerals and iron associated to organic matter, soil organic matter. And the ratio between iron extracted by oxalate and iron extracted by ditionite should be equal or higher than 0.05. So I need to register a low content of iron connected to organic matter or connected to low crystalline minerals. The majority of this iron should be connected to hematite or goethite, high crystalline minerals, okay? The other criteria is that this section does not form part of a plintic horizon. So I cannot find plintic horizon and nitic horizons at the same time. Oh, and you can think, why JJ? Why we are considering this? Because of this high content of iron. We are saying that I must register a high content of iron, but to differentiate the plintic horizons, we just, okay, we're not putting both at the same box. We are not putting both in the same section, just to avoid that to register something that express these shiny faces at same time that express some concentrations of iron as plintite or concretions or nodules or anything else, okay? You should remember in this case that, for example, we can combine plintic horizons and argec horizons. So if you find some shiny surfaces and some concretions or nodules, No problem to combine plaintic and argic, but we cannot combine nitic and plaintic horizons, okay? And the last criteria is to identify the minimum thickness. The minimum thickness of the nitic horizon is 30 centimeters. This thickness is high as in the ferhalic horizons. It's one of the highest or largest thickness that we have in WRB. Okay. Another horizon that also does not express concentration of anything, just have a morphology, let's say a specific morphology that differentiates and express specific process, is the vertex horizon. The vertex horizon also register a high content of clay, but in this case, we does not have clay skins. We have some features that express high activity clays. Some features that express an intense shrinking and swelling and some movement of clay, especially clay in the soil, because of change of volume. So because of the high content of clay and especially because of the high content of high activity clays like smectite, illite, and others, we have a lot of cracks, as you can see here. Some huge structures, like you can see, this is just one pad, one huge prismatic structure with a lot of cracks, and these huge structures and these huge cracks express the sum of the shrinking and swelling process that occurs in these soils. So some of the faces that we see that shine are not clay skins, but they are called slickensides. These shiny faces, like here, and very easily seen here, they express the clay movement of inside the soil. Okay, so because of the shrinking and swelling, we have some mass movement in the soil, some friction movements, and because of this friction, we have some orientation of the clay. This orientation produces these shiny faces, but you still have some like lines, some string lines in this shiny faces that express this friction. Okay, so this friction creates these shiny faces expressing high activity clays. So it's totally different from shiny faces that we can see in the clay skins in the, for example, in the nitic horizon, because here we are talking about a huge surface, as you can see here, a continuous huge surface. Okay, because of huge aggregates that you can see, we are not seeing small shiny faces in concave materials. We can see here more shiny faces in flat faces connected to this friction movements. Okay. Oh, here just a video that you can see that you can just remove some soil and see these lichen sites getting even more clear. Can you see that? It's amazing, right? It's wonderful, this kind of structures. Okay, they express that this soil is moving. Okay, the clay material is moving from above to below and from below to above because of change of humidity and temperature between the sections and the horizons in the soil. And because of this movement, we have some friction between the layers, between the aggregates, between the horizons, creating these lichen sites. We can see a lot of wedge-shaped aggregates as here. So it seems like a wedge. Okay, here, and here. All of these aggregates, they express this clay movement and create this wedge-shaped aggregates that we only can see in horizons that has a high content of clay and also a high content of high clay activities. So let's see the criteria for this specific horizon. First of all, we'll have a minimum content of 30% of clay. We must register a huge or at least 20% of volume of wedge-shaped soil aggregates as I showed you, okay? And they should be titled between 10 and 60 degrees from the horizontal, okay? We should register slick sides on at least 10% of this aggregates, and we must find shrink swell cracks. So like these cracks that we can easily see here, cracks that can disappear during the wet season, but that can be huge during the dry seasons, okay? And the minimum thickness of this horizon is 25 centimeters. We also have the proto-vertic horizon. The proto-vertic horizon is a horizon that already express some high activity clays, but the features are not so clear as the vertic horizon. So we have clay texture, we have a high content of high activity clays, but the expression of this high activity clays is not quite clear yet. So we have similar criteria for the vertical horizon, but let's say that they are less demanding, they are less exigent, they are easier to be fitted. Okay, so first of all, the minimum content is basically the same, 30% of clay. We also should register wedge-shaped soil aggregates, which should register slicking sides, we should register shrink swell cracks, and in this case, and of course, we need to find at least one of them, okay? Or. So wedge-shaped soil aggregates, or slicking sides, or shrink swell cracks, or a coefficient of linear extensibility, that's called COL, of equal or higher than 0.06 per, okay? And the minimum thickness of 15 centimeters. So we have, let's say, less demanding criteria, more optional criteria to identify some high activity clays in the soil with some movements or some materials or some features, but we don't have all the set that could fit to the vertical horizon, okay? We also have now the last horizon, the last diagnostic horizon, the cambic horizon. The cambic horizon, as the cambic horizon that we can see in soil taxonomy, it registers an incipient wafting. So this cambic horizon is something that starts to express some pedalization. So we have pads, we have aggregates, we have a structure that it's at least weak, but usually moderate. So we can see some soil formation, some horizons formation that are not connected to melanization in the A horizon, and it's not a saprolite or something that's connected directly to the parent material, but we don't see any complex process. For example, we don't see any intense chemical wafting that concentrates iron oxides and kaolinites. We don't see any kind of clay movement. We don't see any kind of structure that express high activity clays. So we just have some pedalization. We just have some formation of pads, but we don't have anything else, just that. Okay, this is the cambic horizon. So express an incipient wafting and contrasts with the parent material. So we cannot see any strong influence of the parent material in this cambic horizon. Of course, we can see some, but not a strong influence that shows a weak obliteration of the parent material. So it's not a C horizon, it's a B horizon, but with no complex process, like no argillaviation, no formation of concretions or nodules, no reducing of iron oxides, no migration of clay. So we don't have any other complex process, okay? Something that could express the formation of this cambic horizon is a little concentration of warfarin residues. For example, so we can register some secondary minerals like iron oxides, kaolinite, and others expressing at least a little warfarin, okay, an incipient warfarin. And if this soil that you are studying is formed from warfarin of carbonates or gypsum, the removal, or at least the starting of the removal of carbonates and gypsum and salts from this section, from one section, it's also um, it's also good to identify the cambic horizon. So if you register a soil that comes from the wafering of carbonates, a section without carbonates, or at least with a very low content of carbonates, it's enough to call this section as a cambic horizon because you have the removal of primary minerals, okay? This photo, for example, you can see a cambic horizon with a lot of whitish dots. These whitish dots are feldspar grains. So we have a lot of feldspar grains here, but we still have a lot of kaolinite and other minerals expressing some of this chemical warfare. And just that, we don't have any other process that could express some intense or complex process than just wafering and pedalization, just then the wafering and formation of aggregates and pads. So let's see the criteria for a cambic horizon. The cambic horizon is a mineral material, so the content of organic carbon should be lower than 20%, and it should register a texture class of sand loam or thinner than that, or very fine sand or loamy very fine sand. So I cannot register a sandy texture in an exception if I don't register a very fine sand fraction. Okay, so I can register basically siltic, clay, loamic textures, but the sandy only if you register very fine sand texture, okay, or loamy very fine sand texture, okay. And the soil aggregate structure should be equal or higher than half of that horizon. So at least half of the horizon should be composed of aggregates or pads. And I should register evidence of soil formation in one or more of the following. Compared to the directly underlying horizon, these two horizons are not separated from the from a lithic discontinuity. So the cambic horizon and the underlying horizon, it's not separated by a lithic discontinuity. So they are formed from the same material and just wafering are differentiated then. And I need to find one or more. If the underlying layer has a Munsell color hue of 5YR or rather, a hue should be equal or higher than 2.5 units yellower, else a hue 2.5 units higher than rather, all moist in 90% of the exposed area, or a Munsell color chroma should be equal or one or higher than 1 unit in at least 90% of the exposed area, and a clay content should be equal or higher than 4% in an absolute way than the underlying layer. Okay, or compared to an overlying mineral horizon, 5 centimeter or equal or higher 5 centimeter thick, and they are not separated by a lithic discontinuity. So again, the lithic discontinuity cannot separated the cambic horizon from the overlying or the underlying horizons, okay? And I need to register some colors that express concentration of clay, that express wafering, that express some iron oxides formation at least, okay? Or compared to the directly underlying layer, not showing glacial properties and not forming part of a calcic or gypsic horizon. So I cannot register concentration of gypsum or calcium carbonate, but removal of them, okay? So this removal of calcium carbonates or gypsum should be identified by equal or higher 5% absolute less calcium carbonate equivalent or 5% or more absolute less gypsum and no lithic discontinuity between this underlying layer and the cambic horizon. So as I said, if you have a soil formed from limestones, for example, or gypsum, so because of this material, it's enriched in calcium carbonate or gypsum, the section that you want to call as a cambic horizon should register removal of calcium carbonate or removal of gypsum, okay? So at least 5% less calcium carbonate or less gypsum than this underlying horizon, and no lithic discontinuity, showing that this cambic horizon is formed from the same material that you have below, but the wafering removal some of calcium carbonate or gypsum. Or we have a protocalcic properties or protogypsic properties in the underlying layer, but not in the cambic horizon. So again, no concentration of calcium carbonate, no concentration of gypsum. And these criteria, the letter D, I need to fit all. Content of iron extracted by deutionite equal or higher than 0.1. Show 0.1, showing that you have at least a very low concentration of iron oxides in the soil. A ratio between iron extracted by oxalate and iron extracted by deutionite equal or higher than 0.1, okay? And a Munsell color hue of 2.5YR, 2.5Y, and a chroma of 3 or uh, a chroma higher than 3, I'm sorry. So a monster color hue of 2.5YR, 2.5Y, and a chroma higher than 3, all moist in 90% of the exposed area. All the times that we talk about colors, we are talking about colors at moist conditions, okay? And the two last criteria to identify the cambic horizon. The number 4 is that this cambic horizon should only be classified as cambic horizon as your last option. So the cambic horizon should not fit the criteria for the others. Okay, so I cannot call a section of the soil as a cambic horizon and a Naubic horizon, an anthracic horizon, an argic horizon, a calcic horizon, a duric horizon, phthalic, phragic, gypsic, hortic, hydratic, ehagric, limnomic, molic, natric, natic, petrocalcic, petroduric, petrogypsic, petroplintic, piezoplintic, pelagic, plintic, pratic, salic, sombric, spodic, umbric, pteric, stellic, or vertic horizon, and does not form part of a layer with endic properties. So you see that the cambic horizon should be your last option among all the diagnostic horizons. You need to consider that that specific section does not register any specific process of the soil formation, just pedalization, just formation of pads and aggregates, and we cannot see anything else. Okay, so a limited warfaring, some warfaring that starts to destroy the primary minerals, and because of this, we have some clay. Oh, sorry. And because of this, we have some clay and some pedalization, some pads, some aggregates, just that. Okay, and the minimum thickness to identify a cambic horizon is 15 centimeters. Okay, so with this, we finish all of our diagnostic horizons in the WRB. And now we can see here the reference soil groups. So now, after all the diagnostic horizons, we can start with the classification, the real classification of soils according to the World Reference Base for Soil Resources. Okay, so guys, so far so good. The difference between the horizons, at least you can understand. Of course, as I said, you don't need to memorize all the criteria. It's much more something connected to understanding. But if you can understand, it's quite okay. So let's see how to classify soils according to WRB. The classification according to WRB, it's easier than soil taxonomy because now we have only two levels. So when we classify soils according to soil taxonomy, for example, we have 8 levels. We have a lot of levels to consider, and each level has some specific criteria and blah, blah, blah. Well, in the WRB, we just have 2. And in the first level, we have the reference soil groups, that it's like the type of soil, okay? But the words that you use, with the words that we use is not type, but reference soil groups are just RSG. So at the first level, we have 32 RSG. So yes, we have a lot, I agree. But I think that's quite interesting because now we can differentiate a lot of soils that have different process during their formation. And then considering that at the highest level, at the first level. And in the second level, we add some information in the soil with principal and supplementary qualifiers. So we have some qualifiers that will be added to the RSG and add information. And we can add principal and supplementary qualifiers as much as you can. You don't have a high or a maximum number of qualifiers that you can add. You add if you need to add, okay, if they fit the criteria to be added. And among the RSG, the 32 RSG have some diagnostic horizons and properties that could merge these RSG. And when we think in that way, it's much more easier to understand, okay? And I'm presenting here according to the list, according to the way that we need to classify the soils. So we have some preference, we need to follow some order, and according to this specific order, the first RSGs that we need to consider are the hystosols, okay? And then we go further. So the first are the soils with a thick organic layer or a thick organic horizon. Layers that express the folic or histec horizons, and because of this higher content of organic carbon, we register a hystosol. And after the hystosols, if you don't register a thick organic layer or a thick organic horizon, so then we can think about soils with significant human influence. So soils that were deeply affected by humans. If these humans affected by long and intensive agriculture, so we have the anthrozols. If these soils were affected by humans, but they just have artifacts, just formed by other kind of uses than the agriculture, so we call technosols. So the anthrozols, soils formed by long and intensive agriculture. Technosols, all other soils formed by humans. And after these soils formed or deeply influenced by humans, we have soils with limitations to root growth. Soils that express some layers or some sections that avoid root growing. So we have the soils affected by permafrost that we call cryosols. So soils that register very low temperatures and then the formation of permafrost. And because of permafrost, roots and water cannot migrate to deeper horizons. We have leptosols, soils that are really, really thin or with many coarse fragments. So the R layer, the rocks, the fresh rock, it's quite close to the surface. And because of this, the rock does not allow roots to grow at deeper horizons. We have soils with a high content of exchangeable sodium with the nitric horizon, for example, and we call them solonets. And because of this high sodium content, we know that it should register an intense migration of clay, forming a horizon with a very high bulk density that avoids or at least limits the root growing. We have soils with intense action of shrinking and swelling process because of high activity clays, and we call them vertisols. So the roots cannot easily grow because as deep as you go, you register even intense shrinking and swelling process, and this avoids root growing. Okay. We have some soils that express high concentration of soluble salts, and we call them soil sharks. Okay, and sometimes because of the salts, we don't register a high root growing because of the salt and high electrical conductivity. We also have some soils with some, let's say, particular iron aluminum chemistry, and we call them glacials if they are affected by underwater, tidal water, water table layer with clay properties. We have the endosols with soils with endec properties that express low crystalline minerals as allophane and or aluminum humus complexes. We have soils that express migration of organic matter and or aluminum iron oxides and a concentration then in the subsurface. We call them podzol. We have soils which express it in the past some glade properties, but then the water table level, the conditions change it, and then we concentrate iron as nodules and concretions. We call them plintosols. We have soils with stagnant properties. Yes, soils with stagnant properties, and because of this stagnant properties, we could differentiate them between planosols and stagnosols. We call planosols those soils that register stagnant properties, and these stagnant properties are connected to a huge amount of clay at the subsurface horizon. Okay, so planosols. And those soils that just register stagnant properties because, for example, our layer is quite close to the surface and express this stagnant properties, we will call it as stagnosols. Soils that express a high amount of shiny faces. So I have some clay coatings covering the pads and aggregates, low activity clays, and strongly structured. We call them nitisols. If you register a soil with a dominance of warfarin residues as hematite, goethite, kaolinite, gibbsite, you register a ferrosol. Ooh, a lot, right? If you register soils with a mineral horizon that's enriched in soil organic carbon, you have four options. The first option is if you register a very high content of soil organic matter and also secondary carbonates. You call them Chernozems, the Russian typical soil. If you register medium to low soil organic carbon content and secondary carbonates, so you have the Castanozems. If you register medium to low organic carbon content, just a dark horizon with no secondary carbonate but a high base saturation, you have the Philzems. If you register medium to low soil organic carbon content, a dark surface horizon, and low base saturation, you have the amber salts. If you have accumulation of non-saline substances at subsurface, especially, but also at surface, like for example, silica, gypsum, or carbonates, you have three options. In the case of accumulation of silica, you have the durisols. In the case of accumulation of gypsum, gypsysols. In the case of the accumulation of carbonates, calcisols. If you register a clay enriched subsoil, so if you register some clay movement and some enrichment of clay at the B horizon, you have five different options. The first of all is the ready sols. Ready sols, you have erratic properties. I will show you. You have some interfiguring of coarse and fine horizons, some pieces of coarse and fine horizons integrated to each other. If you have low activity clays and low base saturation, you have the ecrisols. If you have low activity clays and high base saturation, you have the lichisols. If you have high activity clays and low base saturation, you have the alisols. If you have high activity clays and high base saturation, you have the luvisols. And we have some soils and with incipient development, some soils that register a weak formation of soil but still have soil. So first of all, those soils with are moderately developed, so we have some B horizons, can be soils. The others, soils without a B horizon, or at least without a diagnostic horizon that could be classified as a B horizon, okay? Stratified sediments, soils formed by, for example, alluvial sediments, the fluvisols. We have soils with a sandy texture and very low development of diagnostic horizons, arenosols. And the last one, a soil with no significant profile development, the redosols. So these are the 32 reference soil groups that we register. And let me just show you as you can classify the soil. So we have the RSG, and to classify them, you just need to check the criteria for each RSG. Okay, great, this is quite easy. So let's see, for example, that the solonets. The solonets, they are soils that they don't fit the criteria for the previous RSGs, and they also have a natric horizon in the first 1 meter below the soil surface. So these are the solonets. And then I will put the name here. But now I need to consider the principal and the supplementary qualifiers. And we have some differences between them, okay? The principal qualifiers, they came before the name. So we add the letters here, okay? We must add the qualifiers before the name. And the supplementary qualifiers we add after the RSG, and we add then between brands and with comma. Okay, and we need to type everything just with the first letter in the upper layer. Okay, so the upper letter is just the first, and then the low letter we use for the rest as a regular way to write something. Okay, and we also need to consider other rules. When we check the qualifiers, we need to follow this order that's presented, okay? And this order is not following any rule than the importance of that qualifier, okay? So that qualifier, it's quite important to land management, to land use, or express some very important process that format that soil so they are at upper conditions like the abruptic or glaic or stagnic. They are the three first qualifiers in the principal qualifiers. So they are quite important. And when you go down, you see that you register, let's say, less important qualifiers. And you have as the last option the applet. And the HAPLEC, you can only use the HAPLEC horizon, HAPLEC qualifier, I'm sorry, if you don't have any other qualifier. So let's see that I'm describing a soil and I classify it as a solo nets, and I cannot fit any of these qualifiers. So I will add the HAPLEC. So the HAPLEC is the qualifier that I only can use if I don't fit the others. Okay? If I fit any of them, at least one, I will not using the HAPLEC qualifier. And something that's also important, another rule, is that as much you have this qualifier as the main qualifiers or in the beginning of the list, you must to add this qualifier closer to the RSG. So for example, you can see in this case that let's say that, for example, I describe it as soil, that's a solonets, and then I started to add the qualifiers. And I check the abruptic, and this specific soil profile does not fit the qualifier abruptic. So I go to the glaic, and it fits. It fits the glaic qualifier, so I add it. And then stagnic, molic, selic, and gypsic. And when I find the gypsic, it also fits the gypsic qualifier. So I add both here. But you can see that the glaic qualifier, it's closer to the RSG. So the uppers or the most important qualifiers, I always add closer to the name, closer to the RSG, okay? And the qualifiers that are below, they are always in the beginning of the sentence, or let's say farther than the RSG. Okay, so if I have 1, 2, 3, 4 qualifiers, 5 qualifiers, doesn't matter. Those that are in the end of the list, they should be in the beginning of the sentence. And those that are in the beginning of this list should be closer to the RSG. So let's say, for example, that I could add a new qualifier in this example, like the Elbec, okay, the last one before HAPLEC. The Elbec horizon should start here in the beginning of the sentence. So in this case, I should call Elbec, gypsic, glaic, solonets. Okay, so as much as it goes to the bottom of the list, this qualifier should start the classification, should start the name of the soil, should be further from the RSG. Okay, great. So this is quite easy. The second rule that we need to follow is that the supplementary qualifiers now they are also describe it according to that importance, and you need to follow this order too, but you don't need to worry about the order because you just need to follow them. So we always, or at least in the majority of cases, we start with the texture. So arenic, claytic, loamic, or siltic. And with this slash means that you cannot use more than one, at least for the same horizon. Okay, so I can just use one of them at least for the same section. So of course, because does not make sense that I have a section that it register acrylic and loamic textures at the same time. Does not make sense. But I can register a soil with an arenic section in the first, let's say, 20 or 30 centimeters, and below it register a clay texture. So I can express this both textures, no problem. I just need to inform that they are connected to different sections in the soil, okay? So we start, as I said, in the majority of cases with qualifiers related to the texture, and then we go to other qualifiers, and we just need to add them here following the specific list and add comma between them. So let's say that this solonets has a clayic texture. So I add clayic, comma, and then I look for other options and I just find the ocric. So I had ocric here and I just look for others and I found reptic here and I just add reptic. So the name will be gypsic, clayic, solonets, clayic, ocric, reptic. Okay, you will see that some names in WRB could be huge, like we can add a lot of principal and supplementary qualifiers, and because of this the name could achieve a huge size, but no problem because it is expressing a more complex process. I like it very much because shows you that that specific soil has a huge and complex process that we need a huge and a more complex name to show, to express it. Okay, so simpler names will express simpler soils, and more complex names and huge names will express more complex soils. And we can add even more information now, okay? We can add some prefixes to the supplementary qualifiers, to all qualifiers. We can add this prefixes to the qualifiers to express some localization, some spatial distribution of that specific qualifier. So, for example, we have that name, gypsic, clayic, solonets, clayic, ocric, reptic. But according to these prefixes that are just some of them, we can add more information. So let's say that, for example, the gypsic properties, they are only occurring in the first 50 centimeters. So they start at the soil surface and ends before 50, or they start at the surface and ends at 50 centimeters, or they start after 0 and ends before 50, or they start after 0 and ends at 50. So we add the letter epi. So for example, let's say that we have gypsic properties between the soil surface and 50 centimeters. So we just add epi-gypsic. And then we have the glaic. Now let's say that, for example, the glaic properties, they start at 50 and ends before 100, or they start at 50 and ends at 100, or they start after 50 and ends before 100, or starts after 50 and ends at 100. So all these four options also fits what we call endo. So let's say that the Gleick properties starts after 50 and ends before 100. So we have endogleic. And of course, the RSG, we don't use any prefix. And then we add other prefixes to other qualifiers. So let's say that, for example, the clay properties, the clay texture is universal. So the clay texture starts at 0 and ends before 100 or at 100. No problem. I have here the panto prefix. So pantoclaic. The ochric, we don't add to it. And we have here anoreptic. What is the anoreptic? That this reptic, it's connected to lithic discontinuities. So we have lithic discontinuities that starts at 0 and ends after 50, but before 100. So all these two options, we use the ano. So anoreptic. So you can add these prefixes to show the spatial distribution of one qualifier. That's also interesting because now two soils with the same qualifiers, they can register different names according to these prefixes, showing that they also express different processes. They also have different differences of genesis between them. They have the same, let's say, regular name, but the prefixes add even more information. So a lot of people complains about these names because it's quite complex to understand in the beginning. But to me, I think that everything is quite complex to understand in the beginning. The soil taxonomy and other systems, they are basically the same. Each system has its specific particularities, and something it's easy, something it's hard. So sometimes cloudy, sometimes it's sunny. We have these differences in all systems, and we have some things that you need to pay more attention and put more effort to understand. And but it's okay. It's okay to do that with time. Okay. You can ask JJ, should I all the time put the prefixes? For example, no. If you classify the soil according with this, for example, without adding any prefix, it's okay. It's 100% correct. But of course, if you add the prefixes, you are adding even more information. So you must, or at least you should add information as much as you can, but as much as you can. If you cannot add, if you don't feel comfortable, or if you don't understand deeply the differences between them, you just need to check this figure, and you can do very carefully later after you return from the work, okay, after you receive the data, after you receive the lab data. So you can check this with time. I never pay attention for these prefixes at the field without the lab data because I think that's too time consuming. So I prefer to do that after the lab results. So then I can do that in my office, resting with the AC turned on, and I'm spending time and checking the data, and then I can very carefully add all the prefixes. Okay, so at least for me, I don't do that at the field because I think that's much more interesting to do that after the lab results. Okay, so now we can start with the reference soil groups. But before it, let's stop for 15 minutes, okay? So we can rest a little bit, drink a coffee, drink some water, and go to a restroom if we need. So for me now, it's 10:25, 24 to 25. Let's return 10 and 40, okay? So in 15 minutes. Just stop here and Hello everyone again. Let's return. So share my screen again. So now, okay. So let's see. We will start to check the RSG, the reference soil groups in WRB, the World Reference Base for Soil Resources. And following that list, the first RSG that we need to check are the hystosols. And the hystosols are those soils that have one or more of the following. So number one, two, or three. Number one, the registered organic material starting in the first 40 centimeters below the soil surface and having in the first 100 of the soil surface a combined thickness of 40 centimeters or 60 centimeters of organic material according to the nature of this organic material. If this organic material is composed by dead plant residues or moss fibers, so at least for 40%, 40 centimeters or sorry. If the composition of the organic material is any other organic material, it should be at least 60 centimeters, okay? I bold the organic material and I highlighted with red color because you must remember that organic material in the WRB definition, it's a little different from soil taxonomy. Soil taxonomy, we consider that organic materials are those with 12% of organic carbon, and in some specific conditions, we can also decrease this value to 8%. If, for example, we have some human action, okay? So the content of organic carbon to identify organic material in soil taxonomy, it's much lower than WRB. In WRB, we just have one value, that's 20%. So to identify organic material, to identify a hystosol, you must find a very high organic carbon content. And this organic carbon content, it should encompasses 40 centimeters or 60 centimeters according to the nature of this organic matter. Or I should find organic material starting at the soil surface, having a thickness of 10 centimeters or higher than this, and directly overlying ice, continuous rock, or technic hard materials that were added by humans. Okay, so in this case, just 10 centimeters will be enough, but this organic material should be above rock, ice, or something added by humans like concrete. Okay, and the 30 options that I have a layer of coarse fragments that together with overlying organic material, if present, starts at the soil surface and has a thickness of 10 centimeters or higher if overlying continuous rock or technic hard material, or 40 centimeters or higher, and the major part of the interstice between the coarse fragments is filled with organic material, and the remaining interstices, if it's present, are void. This 30 option is expressing some coarse and skeletal materials. So in some soils, you could register huge amount of coarse fragments of pieces of rock, and between these rocks, between these coarse fragments, between these gravels, you can see a lot of organic material fulfilling these voids. Okay, these are the 30 options that we have. So for the all options, we must register organic material. We must register high organic carbon. And we can see a photo that express this in this first 40 centimeters, starting at the surface and ending here. We have organic material with a very high organic carbon content. We can see some cracks that express the shrinking and swelling of the organic carbon, of the organic matter, of the soil organic matter because of the variation. And we have another option. Both cases are isosols. Here we have a soil that's affected by flooding. So you can see here the water of the river, and because of the water table level that's quite close to the surface, you decrease the microbial activity. And because of this very low decomposition, you can store a huge amount of organic carbon and then be classified as a histosol. Okay? Now, let's see those soils that are not isosols. So you can see that here we start with other soils having, so soils that does not fit the criteria for a isosol, and they have a hortic, ehargic, pelagic, or terric horizons with 50 centimeters or more of thickness. Okay, so they should register one of these horizons that express human actions, and they are surface horizons, remember? Or we have an anthracic horizon and an underlying hydraulic horizon with a combined thickness of 50 centimeters or higher than this. Or we have a pratic horizon, the layers of which have a combined thickness of 50 centimeters, if we have a lot of pratic horizons, okay, in the first 100 centimeters of the mineral soil surface. So is the case of this photo. Okay, we have a pratic horizon, in this case with much more than 50. Actually, we have much more than 1 meter. It's 1 meter and 50, and we still inside the pratic horizon. So definitely an anthrosol. Okay, so soils that were affected by humans, especially in the past, by agriculture practices. Okay, here and it's another option: humans producing terraces and producing soils, and because of this, producing anthrosols. So here you already saw this picture related to the construction of terraces. Okay, that humans add some material and produces some specific materials and horizons that shows a strong influence of humans. The terric horizon. Here we have the influence of humans flooding the area. So we have the anthracic horizon and hydraulic horizons. And in both cases, we have an anthrosol because of this huge influence of humans. And we also have humans affecting the soil properties, affecting soil morphology, but not because of agriculture practices, but because of other kind of land uses. So other soils that does not fit the criteria for isosols, soils that does not fit the criteria for anthrosols, and one or both of the following. They have at least 20% of artifacts. What are artifacts? Artifacts are materials produced by humans and added to the soil. For example, concrete, asphalt, stones produced by humans, trash, everything are artifacts. Okay, and these artifacts, they should cover at least 20% by volume of one horizon, and they should be fitted. They should be found in the first 1 meters below the soil surface, or they should be found until a limiting layer. Okay, something that was created by humans and avoid root growing, water percolation. Okay, or they have a layer that has at least 10 centimeters of thickness, and this layer starts in the first 50 centimeters below the soil surface and has at least 80% of artifacts. So if the amount of artifacts increase, so I should register only 10 centimeters will be enough. Okay, but these artifacts also should be closer to the surface. So in the first 50 centimeters. Okay, and so number one or number two, and it should be letter B, I'm sorry, not having a layer containing artifacts that qualifies as anargic, duric, ferrolic, ferric, phragic, hydratic, natric, nitic, petrocalcic, petroduric, petrogypsic, petroplantic, pisoplantic, plantic, spodic, or vertic horizon in the first 1 meter below the soil surface unless they were buried. Okay, so if you register in the first 1 meter in the same horizon that you find the artifacts, properties that fits one of these horizons, so no, it should not be classified as a technosol. Okay, and not having a limiting layer starting 10 centimeters below the soil surface. Okay, or, and this should be number two, I'm sorry, having a continuous, very slowly permeable to impermeable layer constructed by humans with, for example, geomembrane of any thickness or technic hard material in the first 100 centimeters below the soil surface. So if I register number one or number two, I will call that specific soil as a technosol. Soils deeply affected by humans. Okay. These two photos, that one and this one, both are of technosols. You can see some bricks, some concrete, all these bricks, they are called artifacts. And I have a lot of um, spikes and different kind of materials also that cannot be easily seen by this photo, but in the field we could describe. So everything here shows that we have a strong influence of humans affecting the soil properties, and this concrete also fits one of the criteria to identify the technosols. So great, this is a technosol. We don't have any property that could fit the criteria for any of those horizons that we cannot fit. It's a technosol. Great. This is another option. This is a technosol produced by mining activities. Okay, so all of these materials were moved, transported by humans in constructing this kind of surface. So this is other technosol. So another option, now starting with those soils that will have a layer or horizon that avoids or at least limits root growing. So let's see those soils that are not hystosols, are not anthrosols, are not technosols, and have a cryotic horizon in the first 100 centimeters below the soil surface. Oh, JJ, I don't remember what is a cryotic horizon. A cryotic horizon is that horizon with temperatures equal or below 0 Celsius degree for at least 2 consecutive years. So I should register very low temperatures in the first 1 meter below the surface, or a cryotic horizon starting at the first 2 meters below the soil surface, and some evidence of cryogenic alteration like cryoturbation, frost halve, cryogenic sorting, thermal cracking, ice segregation, partner ground, etc. So you should remember that I complained that the definition of cryotic horizon in WRB is just related to soil temperature, and it different from the soil taxonomy, for example, that we also have these cryogenic alterations as features that could classify what they cry the cryotic horizon. Okay, so for here for the classification, this is not a problem because now we combine one of them. Okay, we must identify the permafrost, these very low temperatures, the cryotic horizon in the first 1 meter or in the first 2 meters, but combined with evidence of features that express this permafrost, like cryoturbation that I already explained it to you, the migration of clay from the bottom to the top because of differences of temperature and moisture. Frosts have that is this difference of uh, temperature that induce the freezing of some materials inside the soil, the cryogenic sorting. Because of this freezing, we can register some sorting of materials, and it's quite common to see some gravels and pebbles that are quite aligned. They have some orientation because of this cryogenic sorting. We have some thermal cracking. Crackings format because of the solidification of water, ice segregation, that ice tends to segregate clay from the coarse materials. Partner ground that we already saw, those features expressed at the surface because of this ice segregation of fine particles, okay? So this soil, this photo you can see here in 60 centimeters, the permafrost, the cryotic horizon, temperatures below 0 Celsius degree. Here you can see some clay movement, some evidence of cryoturbation. Here also some evidence of cryoturbation. You can see in this photo two cases. Ice segregation, because you can see some segregation of fine and coarse materials, and also some evidence of cryoturbation, like this darkish zone showing some clay movement from the bottom to the top. Some photos of the partner grounds that express the orientation and segregation of material. Some of these black spots here, here, that express the cryoturbation and the mixing of organic materials inside the soil profile. And we also have some soils that does not register very low temperatures, but they have other limiting layers that avoid root growing or water percolation. So soils that cannot be classified as hystosols, anthrosols, technosols, and cryosols, and have continuous rock in the first 25 centimeters below the soil surface. So the rock should be quite close to the surface, the fresh rock, okay? We are not talking about saprolith. We're talking about fresh rock, the R layer. The R layer should be quite close to the surface, up to 25 centimeters below the soil surface, or I should register a huge amount of coarse materials, less than 20% by volume of fine earth, plus that plant residues of any size, okay? Average it over a depth of 75 centimeters below the soil surface, or until you find the rock, the R layer, whichever is shallower. So in this case, for example, you can see that the R layer is not present, but I can see a lot, like a lot of gravels, a lot of coarse material, and the fine earth, it's just this part is less than 20% by volume. Because of this, I still have a leptosol. And norduric, petrocalcic, petroduric, petrogypsic, pisoplintic, or spodic horizons. All of these horizons, they will identify also horizons and layers that has some problems to water percolation, to root growing, but they are more connected to other RSGs, not the leptosols. The leptosols are soils that shows a very limited weathering of the rock, and because of this, the rock it's quite close to the surface, and slash or we have intense erosion, and because of this intense erosion, the rock it's quite close to the surface. So the lactosols are those soils that will have a lot of gravels and or rock close to the surface and none other layer that express root limiting growing because of, for example, cementation by calcium carbonate or gypsum. I think that someone raised the hand. I'm not sure.
Yes, I did.
Yeah, yes, please.
Um, Please, can you put back the slide? I wanted to just ask a question. The
Yeah, of course.
Now, okay,
Um,
in trying to
oh,
classify, yes,
mhm.
yeah, this particular place, yes. Uh, Now, when you say other soils, you are trying to kind of distinguish soils that have similar behavior but are not to be classified as lato soils. Is that what you're saying?
No, 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 no. You are saying that this soils, they does not register any, they don't register any diagnostic horizon that's quite thick, and they does not register a lot of fine earth. So you must think about soils that the rock, the R layer, it's quite close to the surface. As I said, 25 centimeters up to 25 centimeters below the soil surface. So for example, to identify a ferrosol, you must at least 30 centimeters of a ferralic horizon. So you cannot find the ferralic horizon because you must 30 centimeters, and here you must, that rock should be at 25. So you cannot fit both characteristics at the same time. So definitely you cannot find, for example, a ferralic horizon in this condition. So the lactosols are soils that the rock, it's quite close to the surface. Why? First of all, because you have a very dry climate condition. And because of this very dry climate condition, you don't have an intense buffering. So the rock still's there, quite close to the surface, and slash or let's say that, for example, you have a very steep slope. So because of this slope, you have intense and frequent erosion movements. And these erosion movements, they remove a lot of fine particles. So now you have the rock quite close to the surface. So you can still have some fine earth like here, but these horizons above the R layer, above the rock, they are quite thin. Like here, you have less than 10 centimeters until find a lot of gravels and a skeletal property, a skeletal characteristic. We have a lot of coarse materials and very low content of fine earth until you find definitely the R layer, this rock, the continuous rock. Okay? Is now clear?
Okay, yeah, yeah, it's okay. Just I was just trying to say that that means when you say other soils having one of the following and then not during, yeah,
Yeah, sorry. Yes. It's
you
you
are
need to
trying to say
fit
that.
number one and letter A or B and definitely number two. Yes, to avoid to classify them this. Mhm.
Okay, so this will also help to classify the ferry soils. I think is now is it the ferry
Yeah,
soil?
yeah, yeah.
Okay, thank you.
Welcome. This is another example. In this case, we have 20 centimeters, and this is continuous rock, so the R layer. So we have a horizon here that does not fit any criteria, and no petrogypsic, no calcium carbonate, not gypsum or other kind of salts, not petroplintic or pisoplintic horizons, just R, just rock, continuous rock. In this case, a lactosol. And some soils that also has some problems with water percolation, with root growing, and soils that could be called as solonets. These solonets are soils that are not histosols, they are not anthrosols, not technosols, not cryosols. no, they are not uh, the leptosols, and they register a natric horizon in the first 1 meter below the soil surface. Oh, JJ, I cannot remember very well the natric horizon. The natric horizon is that horizon that has columnar or prismatic structures. So as you can see here, and these structures, they are connected to intense migration from the surface to the subsurface horizon because of concentration of salts and especially salt sodium at the surface. And the sodium chemically dispersed the aggregates and induced an intense migration of clay that enriched the clay at the subsurface horizon and create what we call natric. So the natric horizon, as you can see, hardly will yield, hardly will favor root growing at deeper horizons or at least below this natric horizon because of the very high book density. In this photo, you also can see the darkish colors that I mentioned that some natric horizons presents because of this intense migration of clay and sometimes also organic matter from above to the B horizon. They are quite common in drylands, okay? We also have the vertisols, as I said, soils that register a high content of clay and high activity clays. The vertisols also express some problems to root growing and water, not rather water percolation. It's not so hard because we have huge cracks, but definitely to root growing. The vertisols are soils that cannot be classified as hystosols, anthrosols, technosols, cryosols, leptosols, or solonets. So now they register vertic horizon, that's that horizon that register cracks, silicon signs, at least 30% of clay content. You should remember that. And this vertic horizon starts in the first 1 meter below the soil surface. And so number one and number two, at least 30% of clay between the mineral soil surface and the vertical horizon. So I should not register sandy or loamy textures between the soil surface and the vertical horizon. So let's see the vertical horizon starts at 30 centimeters. It's not in this photo, it's just an example, okay? So between 0 and 30 centimeters, I should register at minimum of 30% of clay. So I cannot register like a sandy or loamy texture between the soil surface and the beginning and the start of the vertical horizon, okay? And I should see shrink swell cracks like these ones, and they should start at the mineral soil surface, like here, at the base of a plug layer, a layer that was moved or transformed by humans, or directly below a layer with strong granular structure or strong angular or subangular blocky structure with an aggregate size equal or below 1 centimeters, okay, because of the self-mushing surface. It's quite common on this self-mushing because of the expansion and contraction, the shrinking and swelling of materials, okay? So the cracks, they should start in one of these, in one of these three, or the last option, directly below a surface crust and extend to the vertic horizon. Sometimes these vertisols, they register some surface crust, some crusts of biological material or salts or any kind of material that could precipitate in dry conditions. So below this surface crust until the vertic horizon, you need to find these cracks. They are quite common starting at the surface. So any of this option to find these cracks will be enough to fulfill the criteria, the third criteria to a vertisol. Okay? So these are the cracks that we can easily see in the vertisols. We can see here the silicon sides. So all of them express the evidence of vertisols. Okay, here more photos of the silicon sides and the wet-shaped structure that it's quite common for the vertex horizon. And we also have the solo chunks. The solutions are those soils that could not fulfill the criteria for the hystosols, anthrosols, technosols, cryosols, leptosols, solonets, and others. I forgot all the names now. And the other soils that having a select horizon that concentrates salts. You can see this whitish color because of the expression of salts. Okay, so you need to find salts in the first 50 centimeters below the surface and not having a thyonic horizon in this first one, in the first 50 centimeters. JJ, I cannot remember what is a thyonic horizon. The thyonic horizon is that horizon that express concentration of sulfates or sulfides. So both these groups of types of minerals, they are connected to high contents of sulfur. Okay, so I'm not talking about horizons that express concentration of pyrite or jarosite or minerals that can be easily oxidized. Okay, I can register sulfur. No, because it's more connected to another RSGs that I will show you. Okay, so I cannot see the thyonic horizon and not being permanently submerged by water and not located below the line affected by tidal water. So, for example, located below the line of mean high water springs. So the solutions are not those soils flooded by tidal water or any other kind of water. Okay, they should be emerged. They should be well drained soils, or at least not flooded, or at least not permanently flooded. Okay, so they should register the select horizon, concentration of salts, not thyonic horizon, not concentration of sulfur, and they not be flooded by water table level or tidal water, no problem. Sweet or salt water, no. It's quite common to see in the solar shots these white dots or these white spots expressing the concentration of salt. The solar shocks, they are different from the solonets because they does not register the natric horizon. Okay, the salt just start to precipitate and the dissolution is not strong enough to disagree to destroy the aggregates at the surface and induce the clay migration. So I like to say that the solon shocks are the past of the solonets, or the solonets are the future of the solon shocks. Okay, because after some dissolution of the salts, so the clay starts to migrate and forms the natric horizon. Okay, they are common in really dry conditions, in drier conditions than the natric, than the solonets and the vertisols. We also have now soils that has some specific iron and aluminum dynamics. Let's start with the glaze soils. The glaze soils are soils that does not fit the criteria for the previous RSGs. So they are not fulfilling the criteria for these previous, and they register one or more of the following. Number one, they register a layer that has at minimum of 25 centimeters of thickness, and this horizon starts in the first 40 centimeters below the soil surface and has Glake properties. Glake properties, I already told you, I showed you in this class, are those properties that express reducing conditions, and I have grayish colors with some red dots or yellow dots in the biopores, in the voids, showing that we have reducing conditions at dominant conditions in that soil, and only oxic features close to the voids. Okay, so I should reduce your horizon with 25 centimeters of thickness with glade properties, and these glade properties should be found in the first 40 centimeters. And the reducing conditions in some parts of every sublayer. So if I find sublayers like here, I can easily see that this glade properties starts around 15 centimeters, but after 30 centimeters and after 60 centimeters, I have some change. But in all of these horizons, I can easily see glade properties and reducing conditions because of the grayish colors, okay? Or, and I'm sorry, this should be number two, both of the following: molic or umbric horizons, and this horizon should has at least 40 centimeters of thickness, and they has reducing conditions in some parts of every sublayer. If we have sublayers like A1, A2, A3, from 40 centimeters below the mineral soil surface to the lower limit of the molic or umbric horizon. So I should find these reducing conditions in all these horizons, in all of these sub layers or sub horizons from 40 centimeters below the soil surface and the start of this molic or umbric horizons. You should remember what are molic or umbric horizons are: dark horizons. Molic register high base saturation, the umbric low base saturations, okay? And I must register directly underneath the molic or umbric horizons a layer with at least 10 centimeters of thickness that has its lower limit equal or higher than 65 centimeters below the mineral soil surface and has glade properties and reducing conditions in some parts of every sublayer. So the second option is to find a molic or umbric horizon that's thick and with some reducing conditions, and below the molic or umbric horizons, I also find glade properties and reducing conditions. Or, I'm sorry, this should be number three, permanent saturation by water starting at up to 40 centimeters below the mineral soil surface. So I should find a water table up to 40 centimeters below the soil surface. All of these three options, number one or number two or number three, they fulfill the criteria to find a clay soil, a soil with clay properties as a dominant reducing conditions, okay? And again, just to check, we can see the water here. We can see the glade properties because of this grayish color and some oxic features only in the voids, only around the voids, like a coating of iron tree, because we have some oxygen in these voids. But in the soil, we have the dominance of reducing conditions as clay properties. We also have the endosols, and here the endosols, they have one specific dynamic connected to low crystalline minerals or organic matter, okay? So soils that does not fulfill the criteria for the previous RSG, and they have one or more layers with endic or vitric properties. We already saw what are endic or vitric properties. The vitric properties are those properties connected to vitric minerals, ash, and some minerals produced by recent volcanic activity. Andec properties also connected to ash and recent volcanic activity, but we have some weathering that destroyed the vitric properties, the vitric materials, and now we have low crystalline minerals as allophane and mogolite that has a strong connection with organic matter and produce some specific properties, and also a strong connection with phosphates. Okay, these layers with andec or vitic properties, they should register a combined thickness of 30 centimeters or more than this in the first 1 meter below the soil surface, and starting at maximum up to 25 centimeters below the soil surface, or 60% of the entirely thickness of the soil if a limiting layer starts be, below 25 and before 50 centimeters from the soil surface. So if I have a limiting layer between 25 and 50 centimeters, so this layer above this limiting layer should register at minimum of 60% of andec or vitric properties. Okay, and sorry, this should be number one: no argic, no ferhalic, no petroplintic, no pisoplintic, no plintic, no spodic horizon in the first 1 meter below the soil surface, unless buried deeper than 50 centimeters from the soil surface. So to call something as an andesol, I cannot register these kind of horizons, okay, only andec or vitric properties, unless, as I said, these horizons were buried at a depth deeper than 50 centimeters, okay? I already showed you these photos, these vitric properties with these white dots that are vitric, okay, ash from recent volcanic activity. And I also already showed you this paper, this filter paper with some phenolphthalein that express this andec properties in some soils when I just mix them with some sodium fluoride, and they showed a strong acidic reaction, and because of this they get purple or pink, and you can see the andec properties even in the field. So you can see the vitric material, or you can see this reaction with the filter paper. Both will show you that you have andec or vitric properties, and then you can classify as an andesol. It's the only way to identify in the field if you have this andec or vitric properties, okay? The other techniques are just lab analysis. You can see here some andesols with these materials here, especially here in this yellowish color. You have a lot of andec properties, and here you have several layers of horizons with andec properties because they are connected to different volcanic eruptions, okay, and the people dated then, so you can see the age started around 9.5 thousand of years before the present, and ends in 1886, so quite recent. In different ages, in different times, we have different volcanic activity that add volcanic ash and then andec properties and then vitric properties to these horizons, and because of this we have an andesol. Okay, here is just to show you that these andec properties, they commonly produce some clay skins in yellowish material. So you can see here a very thin layer, and here you can see very easily This clay skins produced by endec properties in endosols. Okay, it's quite common to see then, and I'm highlighting this because it's not common to see clay skins in yellowish materials, but in endosols, yes, you can see. We also have podosols that also have a specific chemical behavior or chemical dynamic of iron and aluminum. These podosols are soils that does not fit the previous RSG, and they have an spodic horizon in the first 2 meters below the soil surface. Okay, the spodic horizon is that horizon that express podosolization, concentration of organic material, organic matter, and slash or iron and aluminum oxides. So you can easily see here and even here with a less darker color, both horizons here starting at 20 and ending at 45 centimeters, and this horizon starting at 45 and ending close to 80 centimeters. Both are spodic horizons. These spodic horizons express concentration of organic matter, and we have a lot of lab analysis to proceed to confirm the presence of spodic horizon, and especially the absence of allophane, immogolite, vitric, and endec properties to classify something as a spodic horizon. Okay, all of the soil profiles are spodosols. They express, in this case, for example, concentration of aluminum and iron below the soil surface, below an E horizon, this Albic horizon here. And here is the same. You have both horizons that concentrates iron and aluminum oxides below an Albic horizon. Okay, but here we have, of course, some of organic matter too. And we have also the plintosols. The plintosols are those soils that does not fit the criteria for the previous RSG and have a plintic, a pisoplintic, or a petroplintic horizon in the first 1 meter below the soil surface. So let's see. This photo shows you the plintic horizon. You have some iron concentration because this soil suffered in the past some water table fluctuation. So in the past, this soil was affected by reducing condition, but then the water table level gave some space to the oxygen, and because, for example, some tectonic movement or some climate change, the water is not flooding this area anymore. So now oxygen is entering in the soil and starts to oxidize the iron, and we have a lot of plintites, a huge amount of plintites that has this reddish or yellowish colors, expressing a new concentration of iron because of this oxidation, and then a plintosol with a plintic horizon. In these cases, in these two photos, I have here a pisoplintic horizon and here a petroplintic horizon. A pisoplintic horizon, you should remember, will have concretions and nodules, but they are not continuous cemented layer. So the roots can grow through the horizon. The water can easily percolate through the horizon. And here we have a petroplintic horizon, a continuous cemented layer that does not allow root growing, does not allow water percolation through the horizon because section of the soil was deeply cemented by iron oxides. Okay, guys, before we keep going, I will stop here because we still have a lot of RSG and we already talked a lot about them. Let's keep going in the next week with the rest of RSG, okay? Just before we end here, I would like to say some words. I check at that. Okay, I check at that some people replied me about the invitation for the field work, but only two people replied. Okay, so I think that we can do this field work with my own car. I'm just checking with the department. How can we do that? As soon as they confirm about this, I will talk with these two people that confirmed their availability to the work, and then we can do the field work. Okay, but anyway, I first of all I need to confirm with them. I will not planning to use transport from the university. I think that will be even easier for us. Okay, don't worry about that. For those that cannot attend the field work, no problem. We will try to record the field work. I'm not 100% sure that we'll be able, because sometimes it's hard and some places we stop and we cannot hold the camera, or at least the microphone does not work very well, but I will try to do my best. Okay, and I will ask also the students that will attend the field work trying to do that. And okay, let's try to do our best. Okay, is that
Okay,
okay?
okay,
Yeah, it's
okay.
okay. Just, is it possible to confirm those? Because I don't know whether to confirm those who are available.
I'm not sure yet. I
Don't know
need to
whether you
check my
got
email.
my own mail, because so that in case some persons, wrote sent a mail and they probably did not see
Okay.
it, but I will be
Okay.
sure that it's everybody that replied or responded to your message that.
Okay. Maybe it will be easier that I reply to people that I saw the emails, because
Okay.
as I said, just two people. And if I don't reply your email, just send me. Okay. So I will do this right now. I will reply people, and then we can check this. Okay.
All right. Then secondly,
Okay.
please, the slides for the other, you have not posted, updated, uploaded the
Oh,
slides.
okay. So I will do both.
It,
So
I've
let me
been checking
just
and
take
checking
this notes for this. Yeah. No, I know that they helps a lot. So
yeah,
the slides and the confirming
because of the
email.
information that we need from there. It's very important.
Yeah, of course, definitely. Mhm. Yes, Aiden. Yeah. You open at your microphone.
Yes, I thank you very much for the wonderful presentation, sir. I really want to be part of this field work, but I'm really, really sorry because we are not in the Brazil. But sir,
No,
maybe
yeah. No, yeah. I hope so. I hope so. Definitely. I totally understand, guys. If you are not in Brazil, it's not easy. And even if you are in Brazil, but you are quite far from Viçosa, I understand too. So don't worry about that. Okay. As I said, we will try to do our best, trying to record or at least making some notes for those that cannot attend. So don't worry about that. Okay. Democracy, do you want to say
Yeah.
something?
okay, okay,
Yeah, yeah.
okay,
I'm
sir.
also far from Visoza.
Yeah, no, yes, I totally understand democracy. Don't worry about
Okay.
that. As I said, of course, it's quite interesting and important to attend this field work, but I totally understand if you cannot attend. Okay, I know that's quite hard to achieve Visosa, and especially if you are foreign that does not live in Brazil, it's impossible. Let's say in this way, but don't worry. Okay, I hope in
Okay,
the
okay.
future we can do that. If it's not possible,
Yeah.
no problem. We'll try to do our best to show this. Okay, for those that cannot attend. So don't worry. Okay, it's not a problem.
Okay. Share the today's lesson slides and these videos.
Yeah. I shared the last videos, and today I will upload this one too. So I think that will be everything okay. Okay.
Okay, okay, Professor.
Okay,
Have
guys.
a nice day. See
Okay,
you.
okay. Okay, great, guys. So, well, thank you very much for your time. I hope you are doing well. And any doubts, just let me know. Okay. So, see you.
Ciao,
Bye
ciao.
bye.
Thank
Okay.
you. Bye
Thank
bye.
you.
Ciao.
Ciao.
Ciao. Stop the recording.